Hey guys, this is a solution video to the whiteboard, a Looney Beam. So in this problem, we have a massive beam, which is being held in place by the application of a tension force at the end, and fixed to pivot about a nail of some kind, 1/8 of the distance from the end of the beam. We know the total length, and we know this angle. So the first thing we want to know is what is the tension in the cable. Like any good Newton's second law problem, we need to start with a free body diagram. So there's my diagram. I'm going to start adding forces on it. I have a tension force right there. I have a gravitational force because this thing is massive. Where does the gravitational force act on? It always acts at the center of mass of an object. So for an extended object, yes, there is gravitational force acting at every little mass along this object. But if you recall, we can take that the gravitational force acts only at the center of mass and at no other location on the object. So I can throw gravity right there. Now I must have another force, not only because there is an interaction between the pivot point and the beam, but also because if I had only those two forces, this thing would not be in equilibrium. It would be going up and down or rotating or something. So I'm just going to guess that this force is off in that direction. I'm going to call it P. So after I get my free body diagram, the next step is to write down Newton's second law. So there's the sum of the forces in the x and y directions to be 0, but recall that in this section on statics in N5 in our textbook, we now have that if the object is not rotating, we can also use the sum of all the torques to be 0. Now, which of these equations is going to be most useful for us when we want to find the tension in the cable? Well, I would be a little bit worried about trying to use the sum of the forces, because not only do I not know what T is, but I also don't know what P is. And even worse, I don't know what angle P is acting at. I really don't know anything about P. So I can imagine trying to write out these forces, but I also imagine it not being very productive. So let's go ahead and try to write out the sum of all the torques on this object. So that's the torque due to the tension, the torque due to gravity, and the torque due to whatever that P is. Recall that the magnitude of a torque is the distance between the point of rotation and the application of the force times the sine of the angle between them when they're arranged like that. So by picking my point of rotation to be point P, we can see that actually the distance between point P and where P applies at point P is 0. So that means that the torque due to the force P is going to be 0. So once I set that to be 0, I have an equation which just relates the tension torque to the gravitational torque, and I can find everything I know about the gravitational torque, so I have only the tension torque to worry about. So this is now my equilibrium equation. Just using the definition of the torques is going to be the next step. So this is the distance between point P and where the tension is applied, times the tension, times the sine of the angle between R and T. This is the distance from the point P to the center of mass, times the force of gravity, times the angle, sine of the angle between those two vectors. So I need to label my picture to correspond with my labeling here. So I have the distance between P and the application is RCM, the distance between P and the application of T is RT, and then I have the angles, that's phi T, and this is going to be phi G. So I can work those out over here. The distance between P and the application of T is going to be L minus 1/8 L, so it's going to be 7/8 L. For the center of mass is a little complicated because we know the center of mass is right here. It's L over 2 from the ends, but from P to the center of mass is going to be L over 2 minus 1/8 L. That ends up being 3/8 L. So for the angles, the first thing to notice is that since that line and that line are parallel, the beam is bisecting them, and that angle is going to be the same as that angle. So in fact, this phi G, that's just going to be my given theta. And since I have the theta over there, I know that this phi T is actually going to be 180 minus theta. So I'm just going to plug all those things into my torque equation. And now I'm going to make a simplification. It's actually true that the sine of 180 minus theta is the same thing as sine of theta by itself. You could have recognized that, and that makes this problem quite a bit easier because then we have a sine here and a sine here, and those cancel. You could also have just left these like this and done sine of 180 minus 75 sine of 105, and the sine of 75, those two are actually the exact same due to the trig identity. So either way, it ends up in a simplification of the problem. And we also have an L in both terms, so that L drops out, and we end up with something that's pretty simple. Looks like that, and now we can just solve for the tension. That is 3/7 mg, which works out to be about 105.1 Newton. So that's the answer for part A, the tension in the cable. So part B to this problem is to determine the horizontal and vertical components of the force acting at point P. So I want to get back to my free body diagram, and this is pretty typical of these kinds of problems. First find some force acting on the beam, and then after you have that, go back and try to figure out what force the point of rotation is being acted on. So there's my free body diagram. Now I know that the tension is 3/7 times mg, and the only equations I have left to use are Newton's second law, which are now some of the forces are going to be zero because the thing is in equilibrium. To do that, I first got to give myself a coordinate system, so I'm going to do x, y like that. And also, just to simplify notation a little bit, I'm going to break up p into px and py. I could have put an angle on here and then said px is p sine theta and py is p cosine theta. I'm just choosing to leave it in component form like that. Okay, but now I'm ready to just write down some of the forces in the x and y direction. In the x direction, I apparently have only one force right there because F, G, and T are in the vertical direction. So in the vertical direction, I have Py minus Fg plus the tension. Okay, well this immediately tells me that right here, that the force on the pivot is zero in the x direction. That might be kind of a strange result, but actually it has to be that way based on how I picked the tension force. And now I can immediately solve some of the forces in the y direction for the force acting on the pivot in the y direction. Rearranging that equation gets me Fg minus T, which is Fg minus 3/7 mg. And so Py is 4/7 mg. That ends up being about 140.1 Newton. Okay, so that tells me that the pivot is acting actually only in the y direction, and it has a magnitude 140.1 Newton. So that part was pretty easy once we had the answer for part A. So we need to remember what the trick was for getting the answer for part A. So I picked point P using the sum of all the torques so that it would remove the effects of one of the interactions. The interaction I wanted to remove was the nail, or whatever, the pin, holding the beam in place because I didn't know anything about it. So I wanted to first get rid of that, not have to consider that, by picking that to be the point of rotation. If this was a door and I was pushing on the hinge of the door wouldn't move. I could use the sum of all the torques to find out how the door moved by using the other two forces, but the torque due to the hinge is going to be zero, and so by setting that as the point of rotation, I could find the force due to tension. So that's the key, is to pick the point of rotation where the application of the unknown force is. Okay, great. So thank you guys for watching the video, and I hope this helped clear up any confusions about this whiteboard and about torques in general.